very nicely. One is bypass and unbypass. Complete picturization we have seen. For VA infinite, VA not equal to infinite, lambda 0, lambda not equal to 0. All things we'll try to conclude at the short notes. We'll get a good clarity there. Your only idea first try to implement. So we have only two topics remaining so that we can start our problematic subject today. At any stage we will try to complete today. Amplifiers, common emitter. Common emitter and common source. Common emitter and common source today we'll try to finish off so that tomorrow it will be easy to complete the common base and common collector. Okay. So let us continue. Let us continue from here. One of the interesting topic and easy topic also I can say called as fifth module. Active load, which is an integrated concept. Nowadays in GATE exams, definitely this type of questions are coming. So have the trick knowledge. 1 hour you will get all the module now. It's one of the easiest module I can say. Active load concept. Active load concept. A very interesting topic and very important for GATE students. Hardly takes to explain you around 1.4 max to complete this module. Let us see step by step how to do this module now. Okay. Let us understand this module. Active load. Already in previous class in somewhere in NMOS inverters you have seen active load. Active load is nothing but replacing a resistor with a load. I'll show you some introduction for that to understand better. See the idea. Today what I'm doing is some introduction you can see. Some introduction I'm giving for this topic. Till now we have seen two types of amplifiers. One is suppose if I draw like this. This is C, this is RC. You have the output, we have input. Okay. If you do like this, where emitter point we don't take in resistor here, that is RE is equal to 0 we have taken here. We call this as common emitter bypass amplifier I said in the class. So whenever I see the circuit like this, we call common emitter bypass, easily you can recollect. So today class in active loads, how to find out the voltage gains in the problems now. We know basically the formula for this already we derived it. So why can't we have practiced straightforward? The voltage gain which we have practiced it as minus GM into RC. It's very simple formula like this. So this is called a common emitter bypass formula. Minus GM times of RC is our open loop amplifier. Now what I am going to do is the same amplifier. Suppose if I replace like this, emitter is ground directly here also. What is active load concept is in place of keeping resistor here, we'll keep some active load here. Keep some active load, which is called transistor we want to keep. We want to keep a transistor there in place of a resistor. Here resistor is there, here the transistor is there. Definitely for any transistor we can find out some, what I can say, Rx equivalent for that active load. Because an active load is working like a current source, a practical current source. A practical current source will have some resistance parallel to that. The parallel resistance we'll treat it as Rx today. That Rx how to find out for your transistor, which is nothing but output resistance calculations. One time if I know this answer Rx of this transistor modeling, I'll just throw this answer model like Rx here. Okay, in place of transistor we'll keep Rx there. And we'll just write the answer. This is also a common emitter bypass only. We'll recognize that it's a common emitter bypass. And we'll just write the answer as minus GM into Rx. So this is the change in the gain. So one transistor is depending on passive load gain. One transistor is depending on active load gain. Your talent is today how to find out that Rx for a given transistor as a load. That is the analysis today. I'll teach you in different ways how the models they'll ask you, what are the tricks behind that. We'll try to understand. So this is one way of understanding. And another concept is, chance number 2 is, suppose if you have a transistor like this, we have RE, this is VIN, and we have VCC, this is RC, this is output. Suppose if you see this circuit, the second circuit is just looking like a common emitter and bypass, where RE is not equal to 0 here. In this case, your RE is not equal to 0 here. So whenever RE is not equal to 0, we call the circuit name as common emitter unbypass, which is a closed loop amplifier I said in the class. One is a bypass and one is a unbypass. Unbypass gain will be different, which is minus GM into RC divided by, in the denominator we are getting some extra factor, which we derived in the class today. It is 1 plus GM times of RE. So this is our standard formulas, which we can recollect so many times. So this formula we'll never forget, I'm expecting. Minus GM into RC up to that is previous formula only. Denominator you have to practice as same GM you write, RC plus you write RE there. Just 1 plus. That is the way how to recollect the formula. Okay. So what is active load here means? Active load, you want wherever you want you can keep. This person is telling that active load you can keep at RC, you can keep at RE, wherever you want you can keep. Suppose I kept my transistor active load like this. I kept my active load here. Active load. This is my active load. And I kept here also active load, suppose. So both sides I kept active load. Base C, this is VIN, this is your output. Suppose like this I have given a concept. Load means you can keep here also, you can keep here. Wherever resistor is there you can change it to active load resistance. Transistors go, you can replace it. Now the point is, what is the output resistance? Seen from here is, we'll take this as some Rx1 we'll take. Seen from here, we'll take it as Rx2. These are your output resistance of your transistor modeling. In AC model, we are going to find out output resistances. Here you replace with one resistance, here you replace with one resistance of your transistor modeling. So then this model looks like Rx1 will behave like RC here, Rx2 will behave like RE in the concept. So this looks like common emitter unbypass. This circuit looks like a common emitter unbypass because Rx2 will come as RE effect and Rx1 will come as RC effect. So what is the formula change here is gain formula. It is minus GM into Rx1 will come here. In place of RC, we have to take it as Rx1 divided by 1 plus GM into RE plus Rx2 will come. So this is how I solve the gain problems. So the only talent for today class is whenever I give a transistors as a load above or below, you must be able to know what is that Rx and Rx1 and Rx2. So today first we'll take the subtopics, each transistor load how it looks, first we'll take and we'll write the AC models for that and we'll find out output resistances and we'll just confirm it and we'll keep in our mind. Like the different models will be there. Nearly 4 type model it is called. So type 1, type 2, type 3, type 4 I am going to explain you. Each type we have one trick for you. Okay? Like that. Each type I'll explain, each type derivation also I'll show you so that the formula will be remaining for a long time in your mind. This model you'll enjoy a lot according to my concept. Definitely you'll enjoy it. Let's see how we can finish this active load problems. In workbook there are certain set of questions. Okay? Below 1 minute you will solve all these questions. That much quick analysis I'll explain. First get the concept behind this, then you can enjoy the subject. student may get doubt here. Sir, is it required to take two active loads? Means not required. You can take active load here, you can take only RC, that is also okay. You can take active load here, you can remove active load and keep RE there. You have different chances. Just have taken one possibility. Both loads I have taken. One person can take above load, below you can remove it, passive load only you can keep. Below you can keep active load, above you can take normal resistor. You can do anything. There is no rule that I have to take two active loads. Okay. Possibilities is your according to your application. The choice will be taken. Okay. Anything you can take. Just for example's sake, I am teaching the class like this. Don't worry, you'll understand now. That works. For every type 1 example, one example I take side by so that you'll get a good clarity. What do you mean by that load subloads you will understand. So write these two formulas. Who will study BJT today? MOSFET is completed. Because in MOSFET also same formulas. So any one idea is important. If BJT if you know, MOSFET will be easy to solve the same questions. So I'll teach with BJT. Okay, we can convert that in short notes. We'll convert MOSFET formulas. There I'll give the short notes for you. Otherwise here only conclusion I'll explain you. In BJT to MOSFET, what are the changes? So are you ready now? Shall we start without wasting the time? We'll finish this and we'll go to one more frequency response topic is also there. So we have two jobs to complete. Yes, here Rx is nothing but, I can write a point here. Rx is nothing but output impedance of active load you can write. Here Rx, whatever I am solving for each transistor, it is output impedance of active loads in our class. Okay, it's output impedance of active load. It's output impedance of active load. So let us start our first topic. Keep the heading type 1. Type 1 I am explaining. Active load types, you can see. The first load I can design like this. We have a transistor. And something is there above. Here it is collector. Suppose I want to know what is Rx from here. At that time, this is V bias. So this is the way I have taken a separate load side by. First we'll analyze the equivalent model of this, then I'll tell you how to join to an amplifier. Side by I'll give an example of loads. First, this is my load suppose, I'm seeing in the class. In my amplifier, this is a subload, okay? A load layer. Where in this load, the person is asking you, at the collector, you want to know what is the output resistance, because he's seeing from the collector point. And one more thing, V bias is very important here, which is called a DC voltage given to the transistor. If you don't give bias voltage there, the transistor is cut off. It will become active load when you make it active. That means it should work in active region, then it will become active load. That's why compulsory here, some biasing voltage have an extra battery for it, so that the diode will be on and it will become active. So V bias is nothing but a DC actually. V bias means DC voltage. So see the point. First what you have to do is, this has to be done in, this analysis should be done in AC analysis, first point. These all things we are doing in AC analysis called Rx, output resistance we are calculating in AC. Whenever you've done AC analysis here, this model will change like this again. The model will change nicely. So Rx we are fine. You can see what happened is, your V bias voltage, I made it as 0. So for AC analysis, when you calculate the output resistance, your DC voltage should be grounded, that is rule number 1. So I made a DC ground, first step is completed. Okay, after completing that step, can you write this transistor equivalent model in AC analysis? That is AC model we have to write. AC model is very simple. Here R pi will come, here current source will come. That is called the story of your technique. What I can say is AC model. If I want to write AC model for this, AC model, in that we are considering here VA, suppose not equal to infinite I am considering. I am taking the class for VA not equal to infinite. Practical situations will try to understand the loads. If VA is not equal to infinite, the model can be shown like this. This is ground, this is ground, this is R pi. You have an R pi here between base to emitter. The next we have is a current source, Gm into V pi, and there is a resistance here, R0, due to early voltage, and this is your collector point. He is asking you, can you calculate Rx from here? He is asking you Rx, how much for this AC model? So can I say that the story is very simple? These calculations are very beautiful to understand. This is V pi actually. Okay, this is V pi. The same V pi is here. But if you say here V pi, this is ground you have done, this also you have done ground. So I think this answer will become 0. V pi will become 0 because both sides we don't have any potentials. So Akash Mishra, I think now have you understood? Current mirrors, why we use in electronic sales to create active loads. Okay, the transistor want to become an active load, we need current mirrors. Current mirror is a biasing circuit we have used to make number of active loads in our classes. So at this point, these loads we are using. Okay, using current mirrors also we can bias it. Here I said some V bias, current mirrors bias कर सकते हो. Okay, that is application of current mirrors. V bias it, current mirrors bias कर सकते हो. So V pi becomes 0. Therefore Cm into V pi also becomes 0 here. So both will become 0. Means this current source is open circuit. So this current source is open circuit. If the current source is open circuit, what is the Rx value here is? Your Rx is nothing but simply R0. So this is the secret of your Rx value. So whenever I found collector wise the Rx value now onwards, it's a very easy derivation. Rx will become your R0. If suppose early voltage is said infinite, suppose if early voltage is infinite is said, then Rx will become infinite. Okay? This is for VA not equal to infinite. If suppose Rx will be equal to infinite also will come when VA is equal to infinite. But most of the times they ask for VA not equal to infinite, so R0 you can have practice. What is the formula for R0 here is? Where R0 is nothing but early voltage by ICQ. Early voltage by ICQ is nothing but R0, which we studied in our previous classes somewhere called early effect. There I have explained you this total content for about 1.5 hours. 2 hours it has taken time for us. What is early effect? All these things are taught in BJT device analysis. So anyway, this is the story. Now today class, an example is important to understand this. For this, I'll take one example to give clarity for you how the question will be. You can see. Suppose if I take, this is your transistor, this is your signal. We have here RC. This is your supply VCC. You take this as Q1 transistor. Next we have Q2 transistor here. This is your V bias. V bias. This is collector. So we are taking care is output. If you see this diagram, the problems will be given in the exams like this. The same circuit, this active load, I kept somewhere in this board. So how to recollect where is my active load? Which is my active load, which is your amplifier. Because the amplifier will have your transistor, load is where it is, how to identify. If you see that this Q1 transistor, we are not applied at DC, we have applied here AC. So wherever you apply AC, the transistor will work as an amplifier. Okay? That means Q1 is playing a role of amplifier. But if this is amplifier, I think below this you applied some V bias to make it as an active load resistance. So this will be identified as a load in the class. This is identified as an active load. This is active load in the class. That means in place of capital RE, you kept a load there. So that load will be represented with the output resistance Rx we are finding from here, which we found it as R0 in the class. Okay, every time in the exams we should not derive all these things. You have to just keep in mind that collector wise whenever you solve, the output resistance will be R0. Straightforward answer. The straightforward answer is R0. Then what will be the answer for this? It is looking like a common emitter unbypassed it is looking. Because we have RE also, we have RC also. It's a common emitter unbypassed array collector. What is the formula? Just applied. The formula is minus GM times of RC is RC only. Your RC load, I kept RC only there. But 1 plus GM into which GM you have to take is first transistor GM1 you can take. Always your amplifier, which is amplifying the transistor, that GM you have to take. GM1 is your gain is coming. And this is Q2 transistor. So for Q2, we have this R0. So just keep that R0. So can you see that this is the formula of AV in the class? Minus GM1 means the Q1 transistor GM we have to take into RC divided by 1 plus GM1 into RE. This is playing a role of RE. That RE is nothing but I investigated is R0. The problem is completed. So that is the reason I'm telling you this module will be a good grip for you to recollect the formulas very well. Okay. So I think this is my example for this explanation called active load type 1. So whenever you see now on boards at the collector point, you just write R0 there in the class. R0 will be the output resistance, equivalent resistance for your transistor. So this completed the first example, type 1 is completed. Next I'll go for type 2 with some example again. Like the 4 types I'll explain you. Who will understand these 4 types? I think nothing is there in the exams. Any question I can answer it. Pandit, what is the function of active load is? Active load have some advantage actually. What is that advantage means? Conclusion में बताता हूँ, advantage is finally बताता हूँ. First complete कर दीजिए. At the final touch I'll tell you why active loads are better than passive loads. एक meaning बताता हूँ उनका. You'll understand more better in the class. I'll give a good example also for it. At this level, just to understand the concept. First concept is important. Advantage will be easily you can understand when I teach. So first type is completed. Type 2 is my next idea, we'll see. So please write fastly, just I'm waiting for it. Syllabus थोड़ा fast करना हम, okay? We are in slow process. Because around 7th or 8th they are giving a schedule for me Jaipur, so hectic हो जाएगा हमको. So Monday onwards will take long hours to complete the schedule by 7th or 8th because I have immediately some schedule again. Jaipur जाना मेरे को, अभी मैसेज आया मेरे को. Around 7th को complete करके 8th I have to go at 9th approximately. So we'll take long hours from Monday onwards, okay? Daily we are taking only 7 hours like that. थोड़ा increase करते speed, around 9 hours like that daily if you take. By 7th or 8th we'll finish off, okay? Last 2 we should not have any tough to complete it. If you have speed up now, at the end it will be easy for us. Yeah. Jahnavi, what you said is correct. Wherever V bias is there you consider that is active load. Okay, identify the transistor as an active load. Yeah, Q2 is the active load here. Next, type 2 I am doing. Type 2. Second type we are doing. See the second style of getting the load. Suppose if you have transistor here, this is emitter, and this is your VCC, and here I have given some V bias. Somebody has arranged your transistor like this. Below this I am connecting some amplifier now. I want to know at this emitter point, what is your Rx? Sometimes you will get a situation where emitter you have to find out the output resistance. Till now we are finding from collector. Now sometimes it will come emitter because amplifier will keep here now. When amplifier is here, your transistor is above, so we have to see from emitter the output resistance. So situation wise, the position of the terminal will change. Collector wise, whatever the impedance you have will not be same at emitter because emitter is forward bias, collector is reverse bias, so impedances will change. Let us identify what is the impedance for this. Okay, who is this? Akshat Kumar, if you are not, due to some reasons, if you are not getting that link in the type 1, in type 2 also I'll explain the same story. Try to understand here. Okay, same procedure. Here, at least you understand here. If you are not understood the type 1, okay, you have one more thing. Yeah, see here, AC analysis, first you have to apply the AC analysis, seeing the diagram. Whenever you apply AC analysis, what is the story I told you? DC, wherever you see, that should be grounded. So I think you'll see ground here. This is your transistor, this is emitter, and collector also will become ground. That means here, V bias is 0. And here VCC also becomes 0. So this is the common sense. Seeing the port you can do like this. VCC is also a DC battery, that is also ground. V bias is also a DC battery, that is also ground. So 2 grounds we are getting in the problem. So not only parallelly, there are 2 grounds. There will be ground array, VCC also getting ground. Now if I write AC model, next step is AC model. One of the easiest topic here, don't get tension on this module. I'll enjoy this module very well. So this is ground, a beautiful concept. This is R pi. Next we have is a current source, GM into V pi. Parallelly we have some resistance, R0, and we have ground here. And here we are finding at the emitter point the output impedance. So this is the way I'm saying the AC model for it. From here to here is R pi. One side is ground, one side is emitter point where you want to solve from here. Gm into V by R naught and ground. This is your VA not equal to infinite. In every problem I'm solving for not equal to infinite. Because equal to infinite means infinite is coming. So most of the questions will come with not equal to infinite. VA is not equal to infinite. Okay. So AC model 2 is completing nicely. Now you can have a testing concept here. If you want to find testing here, one simple logic you can see this point and this point. If you see this is ground, this is emitter. Carefully observe it. This is emitter, that is ground. Then this model can be represented like this also. Simplicity case, I can do like this. This is R pi. Next we can have a current source. Gm into V pi. Simply make this as ground without writing R naught. Here what I'll do is I'll take some voltage, testing voltage called V naught, and I'll keep here I naught like this. And what I'll do this R naught value is I'll keep it side by like this, where R naught is bended to ground. The same R naught go I just bend it to ground. Without keeping like this, I kept it down. So can you see that this R naught will become the load for you? So let us find out the impedance from here to here first. So you take this as some RA impedance. You find some RA there. After that we'll find out the RX. We'll find out. This is RA. After getting this RA, we'll find out RX, including with R naught. Okay? That's why R naught go just leave it for some time. Only take this modeling and first solve this RA how much. So this is called testing voltage, testing current. So we can have one current this side is a V pi by R pi, which is the base current. One current will flow this side. And another current is I naught is going inward, and this current is also going inward. All currents are going inward. This current is going inward, this current and this current. Why can't you apply KCL at emitter point? Nicely apply KCL. If you apply a KCL at emitter point, it is V pi by R pi plus I naught plus Gm into V pi is equal to 0. So I just applied a KCL that all currents are entering should be equal to 0. This current is entering, and the Gm into V pi, that is also entering. But have you seen one trick here? If you apply the KVL here, in this loop, this is your V pi. What is the KVL trick here is, your V naught will be equal to minus V pi in the class. This voltage and this voltage will be same with the negative sign by using KVL techniques. So we can replace V pi with respect to V naught like this. Minus V naught by R pi you can write, plus I naught minus Gm into V naught is equal to 0. Therefore, I naught is equal to V naught, you can take common, 1 by R pi plus Gm. So nicely you can see the derivation we got. So we can solve the Z naught. Output impedance is how much? It is V naught by I naught. So the answer is 1 by R pi plus Gm. So Z naught value is ZA, I think this is ZA we have taken. Sorry, RA we have taken. Don't confuse, this is RA we have taken. RA value, we got it as Gm. So it's a parallel combination. It is R pi parallel to 1 by Gm. So this is the story we are getting. That 1 by R pi plus Gm in reverse manner is nothing but parallel combination. R pi parallel to 1 by Gm. So this is the story here. Actually we got about RA knowledge. RA knowledge is this one. So if you want not RA, you want RX, then the answer should be RX is nearly completed. It is R pi parallel to 1 by Gm, parallel to R naught. So this is called RX. So from the emitter if you see, RX value is found like this. Okay? The RX value we are finding like this in the emitter side. So this much lengthy answer is not required every time actually. 95% questions, how they'll ask is, they'll try to tell in the problem most of the times. I've seen in the problems. Suppose in the problem he said VA is infinite. If you say like that, you can remove this R naught. R naught will become infinite and R pi is not given in the problem. If R pi is not given, we can neglect it. So like this you will see the questions. Early voltage they'll give infinite so that R naught you can leave it off. R pi will not be given in most of the problems, so R pi can be neglected. So I think we'll get most of the times the answer you can practice it as it is 1 by Gm in realistic manner. This is my answer. This is an exact answer, there is an approximate answer. So approximate answer you can keep in mind most of the times to solve the questions. It's coming a very, very low impedance. So from the emitter side, if you see, you are getting low impedance 1 by Gm. If you see from the collector, you are getting high impedance. That is a very common sense point. Collector is reverse bias, that's why you get R naught. R naught is in the range of mega ohms, close to mega ohms. And 1 by Gm is very, very small. Below 100 ohms, you will get the 1 by Gm value. So one is low impedance effect, one is a high impedance effect. So this is the beautiness of this concept. Nowadays in gate exams for analog students, EC students and electrical students, they are asking this type of questions called network related derivations they are. Okay? Networks basics use करके हम solve करते हैं. So why can't you study first the complete meaning about the circuit? You'll get the confidence on that, then you can go for short tricks. Okay? Unless without knowing these derivations, don't go for the short tricks. First get the knowledge on the derivation first. You get a clarity, then you can start doing the shortcut tricks. Without knowing derivations, all these things if you do shortcut, by chance if the examiner asks you the question like this. Okay? If you forget it, suppose by chance, then I think who has this type of basic knowledge, they'll solve it and they'll answer straightforward. Okay? That's why knowing the derivation is most important here. Thus, again you're asking same story to me. From emitter to ground, I just bended this resistor to down here without keeping like this. This resistor go niche line and the resistor go side में रखकर first ये network impedance find out करो. This total impedance that is RA parallel to R naught will be the final answer. Okay, if you keep R naught, what happens? Mathematics will be tough for you. That's why R naught को side में रख के first network model को complete किया. ये network model को first equivalent calculate किया. After that, I have kept parallel to R naught to complete my task. Okay, that is the beautiness of this concept. So Majumdar here emitter में voltage source is not coming. We are taking. If you want to find anything at one point, emitter or collector output impedance, we'll take some testing voltage there. It's only called test voltage. Okay, we take some V naught as a test voltage. It will provide some test current. With that current to voltage, find out the impedance. This we have to take ourselves. Okay. Yes, Akash Mishra, definitely throughout India, I think I've gone total centers. Okay, maybe I have nearly 9 centers. I think I've seen all the cities. Maximum I covered India. Total cities I covered because we'll roam from one place to other place. I've seen every city. India total covered, maximum covered. So please note on it. I'll show you one example here. Satyam here, V pi is not V naught, my friend. V pi, V naught with a negative sign. Okay, V naught and V pi have some negative sign because this voltage plus this voltage is 0. Then if you take it, V naught will become minus of V pi. It's a negative value. V pi is equal to minus V naught you can take. Okay, I'll take one example side by to understand this better. For every topic you can see one example I'll show you. So that you will get a clarity on the concept. Let us say side by one example also I'll show you. Suppose if I want to design this type of idea, it looks like this. This is your transistor. VCC. This is V bias. V bias. This is Q2 transistor you take. Below this you keep another transistor to ground. This is your VIN and this is your V naught. So this is your Rx. So you can see the amplifier again. Yeah, Satyam, I have seen that also. Okay. Sir, I think Bhubaneswar, I think only that city I have not went. Previous year some other faculty is teaching. Now presently that load I am taking now. So maybe in future I may come to Bhubaneswar to teach. Okay. Let's see what happens in future. So Rx value will be the output resistance we are finding. So I have seen that in this concept amplifier is here, your load is in the top. When amplifier is in the bottom, load is in the top. That means above one is a RC resistance, not RE resistance. So below there is no RE here. So can I write this technique? This is my load. This is my load, which is replacement of RC resistance. And this Rx value you can take it as 1 by Gm2 you can take. Without writing this all things, this total terms, just write 1 by Gm2 is enough, assuming that LV voltage is infinite and R pi is neglected. So 1 by Gm2 you can write simple statement. So what is the answer here? Gain. It is just looking like a common emitter bypass. It's a bypass amplifier. It's a common emitter bypass amplifier. The gain formula is, it is minus Gm1 first transistor into Rx is the answer. The load is Rx here, which is RC. So the answer can be written as minus Gm1 into 1 by Gm2 should be the answer. Can you see the style of answer, how he is presenting? Minus Gm1. Okay. Abhishek is telling Bhubaneswar is awesome city. Great. Great year. In future maybe I am expecting to see your beautiful city. Some teachers said me that is a beautiful city. Great. Nice. AB is equal to minus Gm1 of the first transistor. Load became 1 by Gm2. That is the answer. So this is the trick. You are seeing from emitter here. You are seeing from emitter. Whenever you see from emitter, my Rx value changed. It became 1 by Gm2. So the problem is solved. So the actual load formula is different. Minus Gm1 by Gm2 will be the gain answer for this problem. So complete this as type 2 analysis in the class. So 2 types I completed nicely. Let us see 2 more special models now. Hardly 4 models. 2 models are completed, the basics. So please complete it. We'll come to the 2 more models. In the exam, if they ask you 100% answer, this is the 100% answer. R pi parallel to 1 by Gm parallel to R naught. If they ask you like that, suppose R pi not given, Va is infinite, at the time you can enjoy that 1 by Gms. Like that you can remember that formula. Anupam Das, load is nothing but I am recognizing by this trick. V bias trick से recognize कर रहा हूँ, VIN wherever you go, that is amplified. Above is load, I am recognizing like that. Okay, वो load RC में भी लगा सकता हूँ, RE also we can keep it. Wherever you want you can keep the active loads. And according to that, the bypass or unbypass will be decided. According to that formula will come, formula से हम replacement करें. Yeah, Rahman, I am seeing your chart. Whose resistance is RA? Here RA is the resistance I have taken. Here RA. See here, correct. This RA is the resistance of this total circuit. This network resistance is RA. It is being connected with R naught parallel, that is Rx. First I found this resistance, this complete package I completed. Parallel to R naught will become your Rx. That is the way how I am solving that one. Okay. So please close this matter. Let's see 2 more issues. 2 more issues. Which are the special designs, no? 2 more issues are there. Special issues are there. Let's see that special issues. So, coming to type 3 analysis. Type 3 analysis. In type 3 analysis, the biasing I am doing like this. This is your transistor. Ground I have taken. There is a short here. There is a short, special design it is, short between base to collector. This is your transistor. I want to know what is Rx for this. So correctly if you observe, this type of shorts we have seen in current mirror circuits, correct? In current mirror designs, we have seen this technique called short methods. And not only that, in MOSFET, when you short that, it will become current saturations. So I think BJT will become active region if you short like this. But this type of shorts have some name in analog electronics. They have kept some good name for this. What is that name here is? We call it as diode connected transistors, we call. Diode connected transistor. Whenever you connect like this, we can call this as a diode connected transistors, we call. Why what the name diode connected transistor means? If you see here, base to collector emitter, we have 3 terminals actually, base, collector, emitter, 3 terminals. But base to collector you made it as only 1 terminal. So a BJT is a 2-port network. But when you connect to base to collector short like that, it becomes only 2 terminals. When you have 3 terminals, I can make a 2-port network. When you have only 2 terminals, it will become a diode concept. So diode is a 2-terminal device. So that's why it is called diode connected transistor we call. In MOSFET also you can call diode connected transistor. There is a language which we use. It's a two-terminal device. That's why it is called diode connected transistors. For diode connected transistors, what is Rx value is asking. For diode connected transistors, what is Rx value is asking. Okay? What is Rx value here? So if I want to know what is Rx here, so it's asking from the collector how much the resistance is asking, or not value. So if you see this model, whatever the model you are seeing, just this model, right, it is AC model because there is no DC on both sides. I'm not seeing anywhere DC. DC is already coming from the above circuit, so this transistor is getting on. So no need of pass here. So can I expect now, if there is no DC, just we can write the model directly. AC model we can present straightforward. What is AC model here is, first R pi will be there. This is R pi. Next current source will be there. Gm into V pi. Gm into V pi. And if early voltage, early effect is there, we can write R naught. And finally, we have here collector. Here we can take some testing voltage, V naught. We can take some testing. We can take some testing current. So if we take like this, we can find out here Rx. We can solve the Rx value by taking some V naught, I naught, testing voltage, testing current. We can solve it. But what is the difference here from previous model to present model? Is there any logic is coming here? Means I have seen that in transistors, base collector we never join. Base collectors we never join because there is no contact between base to collector in previous problems. But user what he done is he has made it a single terminal. So now the point is here, a small disturbance you have done in the concept is the base here and this is collector, you simply shorted it. So this is the trick you applied. Base collector you made short in diode connected transistors. When you do like this, whatever the output I have taken here, correctly see, whatever the output you are taking here, the same output will reflect here. That means the input and output both are same naturally when you short like that. So this output will come here. This output will come here. These two will be same. And this current, whatever you are seeing, I naught, this current will divide into three currents. This will divide into three currents. You take this as I1, this as I2, and this as I3. So it will divide into three parts of the current. So now you can find out the calculation. So I0 is equal to, we can write as I1 plus I2 plus I3. You can solve this current relation now. Output current is equal to, three currents are coming, I1 plus I2 plus I3. What is I1 here is, it is V0 by R0 is one current, Gm into V pi is another current, and V0 by R pi is another current. Three currents I am writing. I0 is equal to V0 by R0, one current, plus Gm into V pi, another one, plus V0 by R pi is the next current. But what happened here is, your V pi and V0 both are same, both are parallel to each other. So this V pi, whatever you are seeing, we can convert it as V0 only. So I0 you can write it as V0 in brackets 1 by R0 plus Gm plus 1 by R pi. So Rx value is V0 by I0 is equal to, it is 1 by R0 plus Gm plus 1 by R pi. So if you see clearly, these three resistances are looking parallel to each other. So Rx value we are getting as, it is R pi parallel to 1 by Gm parallel to R0. So you have to understand the secret behind this lecture. So whatever you have been done for the previous lecture, that is type 2, the same result is coming in this. So collector wise you have taken, but it's a diode connected transistor. The impedance is coming just like our previous emitter side, how we calculated. So whenever you take diode connected transistors and you take the output from the collector, the output impedance is very less again. So this is the same issue is coming, what we done in type 2. This is the same answer we got from type 2. Whatever the answer you got, we are enjoying the same answer. Type 2 answer is same. So that way of imaginations you must have to keep this subject easy. Type 2 and type 3, we are getting the same answer. In simplified manner, you can write this answer as Rx value is equal to simple manner 1 by Gm you can practice. For approximate method, we can practice. It's an approximate value. So 1 by Gms you can practice for this. Okay. So then how this question generally they ask? I'll give an example also side by, so that this method also you can easily conveniently you can understand. So how the question they'll ask you can see. There's an example I'm giving for you. And this is Q1 and this is Q2. So if you see like this, suppose the question. By seeing this question you can understand. This is amplifier, this is load. This is diode connected biasing load. So this is your load called active load. Now only I got a secret that Rx value will be 1 by Gm2 you can write. This is the second transistor Gm value you have to take, 1 by Gm2. Then amplifier is here, the resistance is coming here called Re. Capital R plus we got the active load. So this amplifier is called as common emitter, unbypass we call this as. So what is the formula for this is, gain is equal to minus Gm1 into Rc. Rc is Rc only, Gm means Gm1 divided by 1 plus Gm1 into Rx we have to write it. Into Rx we have to write. Where Rx is nothing but 1 by Gm2 and substitute there. So this is the way how this gate questions I can do it. So this completes my package number 3. Show it how this approximation comes with. Thoda idea आप understand करो यार. इतने तक so many topics I taught you. It is R0 is very high resistance. R pi is in kilo ohms. 1 by Gm is in ohms. If you take this complete parallel combination, R0 is in mega ohms, R pi is in kilo ohms, and 1 by Gm is in ohms. Then answer will be ohms or not. That's an approximate value. 1 by Gm is in ohms. Generally, this answer will be mega ohms here. This answer will be kilo ohms. This answer will be ohms. So if you take parallel combination, approximate answer is ohms. Because in parallel combination, answer will be low impedance will come. That's why 1 by Gm will generally consider this an approximate value. Okay. Examiner, if they don't do anything, just I'll write 1 by Gm only. Okay. By chance, if they give R0 also, I'll include it. Until unless if they don't show anything, I'll write only 1 by Gm is enough. Unnecessarily why you write R0 all these things if they don't give the information. you'll understand the question pattern. So this completes my concept number 3. शबनी दास एक क्या क्वेश्चन यार, where we use test voltage कैसे बात कर सकते हैं आप? ये तो क्लियरली बता रहा हूँ, कलेक्टर से चाहिए, कलेक्टर में टेस्ट वोल्टेज किया मैं, आपको प्रीवियस टॉपिक में एमिटर में चाहिए, एमिटर में टेस्ट वोल्टेज अप्लाई किया। क्वेश्चन का मीनिंग क्या है शबनी दास? इतने क्लियरली कॉन्सेप्ट देख रहे हैं, कलेक्टर में देखते कलेक्टर में टेस्टिंग वोल्टेज अप्लाई किया, where you are finding the output impedance, there we have to keep the test voltage. Okay, thank you Harsh. That example definitely will give an idea for how this question will be tackled. Only one topic is remaining, the last topic. That is a type 4 also, I'll explain you. Let's see. शबनी दास, फर्स्ट टाइप में चाहिए तो लिखो यार, लिखो आप लिखो, इधर लिखो, मैं नहीं लिखा आप लिख सकते हैं. This is V naught, this is I naught. Casually I have done it actually. Okay, everywhere you have keep. There is a V naught will be there, I naught will be there. You're seeing from here is R naught. Straightforward I have written the first problem, so I think you got confused about it. Okay, you're solving from here. V naught and I naught. You write in every problem like this. It will become a hobby for you. So please complete the 3 steps are completed. Mondal is asking why Rx pointing downwards. Because you are solving the R equivalent from here. A resistance क्या means इधर से देखता है, ground से देखता है. Okay, you are finding something from top to bottom. You will see from Rx from the collector. I want to tell that you are seeing from collector the Rx value, not from the ground. That is the mean. Okay, आपका किधर से देख रहे हो उधर से arrow indicate करो Rx value. So let us see the final task now. Last task I am doing, which is a type 4 analysis. Which is a type 4. Type 4 is the final concept we are seeing. In type 4, how the situation may come is, suppose how they can do is like this. This is your transistor. This is VCC. This is ground. This is short like this I have done to VCC. And we have something below amplifier is there here. So this point is emitter now. Somebody want to know at this what is Rx value. Sometimes we will get a chance to solve from emitter for diode connected MOSFET. This is diode connected MOSFET. Sorry, diode connected transistor. वो MOSFET भी हो सकते हैं, BJT भी हो सकते हैं. Have you seen the interesting point in case 4 from emitter if suppose comes whether this answer will be same or different? That is the investigation. Okay, both answers same or they are different. Just we'll have an idea whether it will come same or not. Just see the visualization. So first there is a DC source. So AC analysis model you write first. If you write AC analysis model, AC analysis, this will become, this is emitter. This will become ground here, and this is shorted to this is also ground. So you can take like this ground. So you can say VCC is ground here, and VCC is ground here. So like this we are getting the idea. We are getting idea like this. VCC is 0, this also VCC is 0 because both are connected to VCC. If you correctly observe this idea, this model we have already done. We have done this model actually in type 2. This is exactly similar. This is exactly similar to type 2 model. Then why we do the derivation? Common sense apply karo. Type 2 model hai. So what is the answer? We can say in type 2, what is the answer we got? This is emitter and we have ground. Simply you can write direct answer. Your Rx value will be R pi parallel to 1 by Gm parallel to R naught. So the beautiness of this class is this one. Whatever the type 2 we studied is same for type 3 also, it is same for type 4 also, only the first type is different, that is collector of when you view V bias, it is different. In all other cases, smoothly, same answer is coming. That is the beautiness of remembering Act law techniques. So no confusion now. If Rx, if I want a simple answer, approximate answer, 1 by Gm you can take. Approximate answer we can say. Approximate value we can take. So I'll take an example for this. How an example can be created for this model, let's see. So suppose I have given like this ground, this is VIN, VCC, short, this is Q2, this is Q1, and this is your output. Suppose this is the question I designed from this idea. It's asking you, can you tell me what is the gain of this amplifier? First point by seeing this board, I can tell you this is amplifier, this is load. That is a diode connected special load, correct? And where you want is, from the emitter you want to see the load. Emitter, you want to see the load. So just recognize it and finish the problem. So this is your load. You want to find Rx from emitter point, which is nothing but 1 by Gm2 we got. It's 1 by Gm2. What is the gain formula here is? This is a common emitter bypass. Because Re is not there here. So the gain formula is minus Gm1 into Rx is the formula. It is minus Gm1 into 1 by Gm2. So with this, I have been covered the total active load problems. Okay, this much enjoyment you can do about this module. You'll enjoy it. If you see my notes or video, you'll enjoy these concepts. Everywhere blindly, we are getting the answer same. 1 by Gm, 1 by Gm, 1 by Gm. For type 2 also we got same, type 3 also, type 4 also. Only type 1, where we have taken separately V bias, separately VCC. For the type of questions we got at collector point, it is R naught. The remaining any question you see, any type of model, the answer we are enjoying with 1 by Gm. So hardly I think we'll have these tricks in your mind. They will not take 1 minute also waste for these problems. Hardly it takes a matter of 10 seconds to 20 seconds. I can see the option in your books. Okay. So maybe when I solve the workbook problems, your confidence level will increase compulsory. So with this, I have been covered nearly 5 topics. The last topic is the final target today, called frequency response. That will end up the total theory session today. Okay. Maximum 130 or 145. We'll cover the total issues. And afternoon class will enjoy the problematic subject. What we learned till now, we'll apply it. Then we'll get good happiness and good confidence on the subject. Okay. Afternoon entirely we'll do the problems only today. Today, finally we'll complete common emitters. Tomorrow morning, we'll start with the common collector and common drain first. Lastly, we'll complete the common base and common common gate amplifiers. They'll not take much time. Hardly by afternoon we can finish off tomorrow. I'm expecting these issues around 2 o'clock or 3 o'clock. starting tomorrow. 9 to 3 we are finishing. Tomorrow only I want to start a fresh unit. I'm thinking if it completes possibly at 3 o'clock, if it completes, we'll start a new module tomorrow only. That is called multi-stage amplifier basics. Okay. Tomorrow we'll take a lengthy class to complete the issues. Okay. Otherwise, Monday se start karte. Tomorrow common collector and common base at least to complete it. It is Sunday, so Monday onwards will take long hours to complete otherwise. Okay. At least tomorrow will take less time. Monday compulsory will take long hours to complete the schedule. That is how I'm going to start. So it requires a lengthy time for me to teach each and every point for you. So let us complete it. So with this, the total story is completed. So let us start a new point, new topic today. Before starting that, what is the advantage of using ActuLoad? Somebody asked me a question, why to use ActuLoads? What is the purpose of that? I'll give a conclusion for you to stop this analysis. Let's see a small analysis I'll explain for you. Let us see the small analysis for this. Keep the heading, final concept. Importance of ActuLoad. Why you are showing more interest to ActuLoad? A single step analysis. I'll show you an example, you'll understand better. Suppose I have taken common emitter bypass amplifier, suppose. Bypass amplifier with passive load I have taken first. With passive load. Okay? Passive load we have taken, that is RC load we have taken. So what is the gain suppose I want to calculate for this? Gain if you see, this is RC, this is VCC, this is your input and this is your output. You know that this resistor RC cannot be more than 10k resistor. In our classes I already told you RC will play a role of operating regions. It will change. You cannot go more than 10k. If you take more than 10k in DC analysis, the transistors can go to saturations. That's why it's limited for you. You cannot take more than 1k to 10k, the maximum range for it. This resistor you can take between 1k to 10k. You cannot increase these values. It will disturb your balancing circuits otherwise. So suppose here the highest value only I am taking. 10k I have taken is the highest value. And I ask you what is the gain of the circuit. Okay. Suppose GM given in the problem is here. GM is given as suppose 40 millisiemens for BJT. GM is 40 millisiemens are given. So what is the gain? If I ask you, formula is minus GM into RC. So it is minus 40 millisiemens into 10k. So it is coming to be minus 400 we are getting. The answer is coming to be minus 400 we are getting. Suppose if I convert this idea, common emitter bypass amplifier with active load suppose applied. With active load applied called as RX. Let's see what happens. In place of using passive load, my gain is here minus 400. If I use active load, what happened? So active load if I use, this is your transistor, this is your input, PNP I'm using, this is C, this is V bias, this is your output, where this point is collector. So you can use PNP also, we can use NPNs also, whatever you like you can do it. But here, I want to see from collector, that's why I made it as a PNP transistor at the top. So now you can see there's an active load here. This is my active load with PNP design. And finally where you are seeing is collector, you are seeing your RX. Whenever you see RX here, the answer is simply R0. This is your output resistance we are getting in the concept. This is called type 1 model, Rx equal to R0. Okay? But R0 generally, R0 range, if you see, this R0 range, if you see, it is around 80 kilo ohms to 1 mega is your R0 value. This is your R0 value. This much range you have, 80k to 1 mega. If I take the highest value in this problem, if I consider the highest value, then the model looks like this. This is ground, this is VIN. Simply replace this transistor with Rx. That is your R0. We'll take highest 1 mega. So can you tell me, same GM I have used it here, 40 millisiemens. Biasing is same for both the topics. You have same biasing, but load is different. If I convert a passive load to active load, can you see the dynamic range has increased? The secret here is the dynamic range is increased. Okay? The dynamic range, we have increased it to here 80k to 1 mega in the class. The dynamic range has been increased. If you increase 80k to 1 mega, can I expect highest range I have taken 1 mega? Then what is the gain formula here is? It is minus GM into Rx. It is minus GM into R0. This is my active load gain. Minus GM into R0 is the active load gain. How much it is? It is minus 40 millisiemens into 1 mega. So can I expect a milli, if you cancel with mega, it will be around 10 power 3 will be remaining. 10 power 6 into 10 power minus 3 is cancelled, 10 power 3 will be there. So can I expect this will become minus 40 into 1000. You'll get here 40,000 gain. So can you understand at least now why these people are more interested in active loads compared to passive loads? Op-amps wise, we never taken passive loads, we have taken active loads. Not only the benefit is the gain is becoming more, the size is also less. In integrated electronics, the transistor size is less compared to a resistor size in electronics. That's why they have shown more interest in VLSI transistor loads compared to a resistor loads. That's why in advancement everywhere, when you go for analog IC design part concepts, you see always transistor loads, not your resistor loads. Because resistor loads are limited values. But transistor loads are very dynamically, it has a good range. And is having 1 mega ohm of impedance we can bring. So I think it will give a lot of gain for only one transistor I'm talking. 40,000, can you believe one transistor is giving? That is a secret. Why these op-amps are giving very high gain? Because the reason is, secret is very simple. Active load is the reason. So active load will give very high gain. Active load will give very high gain. That is the secret. This is the importance of active load in electronics. Active load will give very high gain in electronics. Just note on it. Just 1 minute, I'll come back. Just note on application. we never connect collector of one transistor to the emitter of another transistor. So we are taking PNP and NPN combinations. Yes, Anupam Das, according to the situation we have to take. Previously I explained this transistor in the bottom. At that time collector we have taken, correct? But again I want collector at the top. We have to change to PNP models. Situation is PNP, NPN is not the meaning. Where you want, according to the terminal has to change. In PNP, what is the advantage is emitter you can take top, collector you can take bottom for PNP transistors. Yes, Akash. Yes, Akash. Yes, so 40 kilovolts will get definitely. But I think in amplifiers there will be some more secrets will be there. Whatever the output will come, it will get saturated to the DC voltage. Okay. Answer will come 40,000 volts, but devices will not give 40,000 volts at the output due to some reasons which we'll try to understand in op amps. Okay. Op amp classes will understand. At this moment, try to understand. It will give very high gain. That is important. So with this, I've been completed successfully our active load subject, which is a separate unit actually, which we covered here only the subject because we got common emitter and common bypass and bypass knowledge. That's why it became easy to teach at this level. Last topic here, which is the final topic for our study purpose, called frequency techniques. Examiner will ask you frequency response also. Okay. So last concept we are teaching. So let us see the final topic. Sixth topic is the final important topic for us. Sixth topic is called frequency response. It is called frequency response. The last topic, which is called frequency response. Frequency response. Today class, I'm going to teach two types of frequency response. One is current gain versus frequency, and the other one is voltage gain versus frequency in BJT classes. First, we'll start with the current gain versus frequency knowledge. There are some interesting terminologies will be there in BJT class. We'll try to understand the terminologies. Current gain versus frequency response with respect to BJT version I'm teaching, so that MOSFET will be similar to that. So current gain versus frequency. Suppose if I take the first experiment, common emitter, short circuit, current gain, you want to find out. This is the experiment I'm doing, common emitter, short circuit, current gain, which we call it as HFE. How we are going to give beta to the user. The designer, what he is going to do, see the idea. HFE, if I want to give for a transistor, how I'm going to do it is, I'll take a transistor first. This is your transistor, and you have some load here actually. At the output you have some load. That load, what I'll do is, I'll keep it 0. Okay, then I'll send a current here, II, and you'll have some current here, I0. This is your transistor. So this is the experiment I'm doing. Your load is short I have done to get the maximum current gain in the class. If you want to get more current gain, load should be 0 you have to take, so that you can draw the more current to the load. So this is called a short circuit experiment I have done, simple experiment. Okay, this is done by non-user, this will be done by designer. We do voltage gain versus frequency in the labs, but current gain analysis will be done by the designer. For what reasons they'll do, try to see. They'll keep a short here, RL equal to 0. When RL is equal to 0, Sushil Kumar, I don't know your part to make up start for it, we'll wait and see the information what they'll give. So V0 will be equal to 0. Your RL 0 means your V0 also will become 0 here. RL becomes 0 means V0 also will become 0 in the class. Now the point here is what is the current gain for this topic is, current gain we can write it as simply I0 by II, output current by input current. I0 by II is equal to HFE. I'm talking here modulus. Here I'm not talking any signs here, only HFE we got, current gain output by input. This HFE will be given by the designer to the user, saying that this is the maximum beta of your transistor. But he's not only telling that beta of the transistor, it is depending on frequency also he's telling. That means that HFE can change according to the frequencies. So that is the mean. So HFE, how it is going to change. So one point you can learn, the frequency response of BJT is a low pass response. Frequency response of any transistor in analog electronics is a low pass response. Have this knowledge. Transistor is not a high pass response, it's a low pass response. The only thing is that transistors will work beautifully at low frequencies. When it goes to higher and higher frequencies, that inside capacitance called diffusion transition capacitance will try to disturb your responses. That's why they call low pass responses. So MOSFET is a low pass device, BJT is a low pass device, op amp is a low pass device. So you should have this basic knowledge first. It's a low pass is telling. Low pass means how the response will come. We can estimate the frequency response like this. This is your frequency, this is your current gain. How a low pass response will come is, first initially you will get a flat band where you have HFE is the gain. Slowly it will fall like this. This is called low pass response. If anybody asks you what is the bandwidth of this transistor, you can take the bandwidth relation like this. Practically, we reduce this gain, HFE value to root 2 times. These are the fundamental rules I'll explain to you today. Why you have to take root 2 all these things. The midband gain has to fall by 1 by root 2 times. Exactly at that time, we have here F beta is a letter I have taken. That F beta is conveying about the bandwidth of your transistor in current gain analysis. This is telling about bandwidth. In current gain analysis. It's not voltage gain, current gain analysis. It is a bandwidth in current gain analysis. Okay? Voltage gain bandwidth can be different, current gain bandwidth can be different. This is a current gain bandwidth. This much bandwidth we are expecting. That means in a decibel scale, if you see, it will reduce by minus 3 decibels delta. That means 1 by root 2. If you apply 20 logarithmic, it will convert into decibel scales also. It is minus 3 decibels you have to reduce if it's a decibel scale in the graph. So what do you mean by this? I'll explain, don't worry. Okay. Here, Parthasarathi, you are saying that when you short this, here not VC knowledge, you are talking about V0 knowledge. Okay, VC is a concept. VC is a concept of DC analysis. Here is AC analysis we are talking. AC wise, there will be some coupling capacitors here which will disconnect your load in DC part. DC wise, VC is there. I kept it at the center of my load line. But AC wise, I'm telling you, load is short in the class. You're not seeing capacitors there. That's why you get confusion. कैपेसिटर छोड़ दीजिए, अब डीसी पार्ट को डिस्टर्ब नहीं कर रहा हूं मैं, एसी लोड को शॉर्ट किया मैंने, ओके? बट यू आर थिंकिंग दैट कैपिटल वीसी इज जीरो. कैपिटल वीसी कैसे जीरो करता हूं यार? कैपिटल वीसी इफ इट बिकम्स जीरो, द ट्रांजिस्टर विल गो टू सैचुरेशन. वो ऑलरेडी फिक्स कर दिया. आई एम टॉकिंग अबाउट एसी पार्ट एनालिसिस, ओके? सो डोंट गो इन द रॉन्ग डायरेक्शन. दिस इज एन एसी एनालिसिस, माय फ्रेंड. DC wise, VC is kept some value, VCC by 2. So anyway, this is called bandwidth. Across 1 by root 2 is taking. There is one more frequency the designer will try to understand. That frequency will come exactly FT, exactly when the gain comes to 1. There is one more interesting frequency our designer will help us to give for the user. So this is one interesting frequency, which we call it as FT, we call unity gain bandwidth frequency, we are calling. Exactly if you touch the frequency, exactly if you touch this frequency, the HFE value will fall to unity there. जाहनवी, I have not explained HFE by root 2 times. कैसे आया मेरे को भी मालूम है अभी. तो एनालाइज ना तो टाइम दो मेरे को. फर्स्ट पॉइंट मीनिंग अंडरस्टैंड करो, ग्राफ का मीनिंग फर्स्ट अंडरस्टैंड करो. ओके, किधर से आ रहे पूरा मैं एनालाइज करूंगा, डोंट वरी अबाउट दैट. ओके, I know that you don't know that. That's why I'll explain. Shabani Das is asking very intelligent question. Why here RL is 0? थोड़ा यूज करो लॉजिक. RL क्यों 0 किया? करंट गेन चाहिए तो वोल्टेज गेन नहीं चाहिए आपको. So if you want to one parameter, other parameter is not required. So if you say V0 is 0, voltage gain is neglected. We have only current gain analysis. So to get the maximum current gain, the load should be 0. Okay? At that time, voltage gain will not affect you. Only current gain will be there in the concept. Okay, Shabani Das? So to understand the simple logic. Current gain, if you want maximum, load should be 0. Because you can draw maximum current when the load is short circuit. So up to here, neatly write down the points. So now I'll define one more graph for you, side by. There's one more experiment I'm doing side by. You can see. This is called common emitter short circuit current gain. Side by, I'm taking common base, suppose. Common base, short circuit. Short circuit, current gain, suppose I have done. Common base, short circuit current gain, HFB. One is HFE I'm doing, one is HFB I'm doing. Just I got an urgent call, just 2 minutes, you note down up to there. दिल्ली से कॉल आया, शेड्यूल का प्रॉब्लम आ रहा है हमको. So we have to complete soon now. So now the speed we have to increase compulsory because the person is telling around 5th only you complete. 5th को कैसे complete हो जाएगा यार? Options is there. I have to teach up to 7th at least. 7th को complete हो जाएगा बोलो. Anyway, we'll plan according to that. In the break time, I'll talk with him because some other subject they are planning for you. I got the latest information is around 15th. I think offline they want to start for you. After completing one more small subject, after analog electronics by 15th, they want to make offline classes for all your centers. Okay? Whatever the centers you said, Patna, Bhubaneswar, Kolkata, these are all centers they are opening around 15th. I got information, so you can expect offline classes may start after 15th. That's why they are making me forced to complete the subject. Anyway, we'll plan it according to that. Maybe tomorrow onwards, I think we have to take lengthy hours. Okay? We should not waste the time now. We have to take long hours to complete the subject. Okay? I'm expecting you will be with me to complete the subject soon. Clear? So anyway, we'll start complete the subject soon. See here. This is the frequency response. Now I'm talking about common base short circuit current gate. Suppose if you take common base design, transistor wise, this is PNP transistor. This is your II. And we have your ground. And here I made short your load. Your RL is equal to 0 I made. This is your V0 is equal to 0. This current is I0. Here I have taken some PNP transistor. For convenience, I have taken here PNP. Sneha Kumari, don't worry, feedback circuit is also there. I have to teach everything. So we'll take long hours to complete the subject. No worries. The others, I think they're planning networks. Okay? They think they want to plan parallelly first. Analog electronics 3 hours networks like that they want to plan. We'll see the timing how they'll plan and we'll try to discuss it in afternoon. After the afternoon break के बाद मैं बताता हूँ plan क्या कर सकते feature. Networks may be the next subject for you, which will be a less number of hours, so it will be completed. After that they want to open the offline classes. Okay? Analog के बाद networks हो सकते हैं. So जल्दी खत्म करते हैं subject को. थोड़ा time ज़्यादा लेकर energy we have to keep more to complete the subject. So what is the current gain here? If I want the current gain here AI, we can write it as I0 by II. It will become here the answer HFB we can write. So one case you are getting HFE, one case you are getting HFB. HFE can also be called beta, we call. HFB can also be called alpha, we call. That means the current gain is not coming same for common base and common emitter amplifiers. Okay, both the transistors. Yes, network is like classes they are planning. Okay, networks they are planning for like. So AI, it will be HFB. HFB is alpha. Alpha is close to 1 and beta is close to 100, 150 like that. So there's a difference between these two. You can see the response. It is also low pass response. Everything is low pass only, but the graph is different, bandwidth is different. So frequency, if you see. So your response is coming like this again. This is HFB and you have to take the bandwidth if you want for common base. It is coming HFB divided by root 2 is coming, which is coming here, some F alpha. So have you understood now? This bandwidth and that bandwidth is not coming same. This is a bandwidth in common base we are getting. This is a common base bandwidth. Here you can write, in place of writing current again here, you can write common base, common bandwidth in common emitter you can write. One is in common emitter, one is in common base. By seeing these two, can you tell me which bandwidth is more? Seeing the board. Roy and Akka is telling Kolkata batch ko already networks is completed. Maybe they'll plan some other subject. Okay, they'll try to divide the centers and they'll write out light. That all things I'll tell you, don't worry. First I should have a discussion with them. Discussion होने के बाद information आने के बाद मैं बताता हूँ. So don't get worried. First start concentrating on the subject. Don't disturb your mind. First concentrate here. Okay, Sneha Kumari, all the subjects are nearly completed. Great. Nice. So common emitter will have more bandwidth or a common base will have more bandwidth. That is a question I'm asking you. Common emitter will have more bandwidth or a common base will have more bandwidth. Common sense use करो. कौन सी bandwidth ज़्यादा लग रही है आपको? So there is one secret here in analog electronics. See here. If anybody say the gain is more, somebody said like this. Anybody say gain is more, then what happens is your bandwidth will come less. Because these two parameters are inversely proportional. If the gain comes more, bandwidth will come less. If bandwidth comes more, gain will come less. You know that beta, HFE is a beta which is very high value, 100 you can take. Suppose this answer is 100 I have taken, just for assumption. So this gain is 100, but HFE is suppose 1 I have taken because alpha is close to 1. You can say this gain is 100, the gain is only 1. So this gain is very high, so bandwidth is less. But this gain is very less, so bandwidth is very high. So what is the secret you have to understand is, this concept you have to understand. As the gain is more, bandwidth will be less. So finally we got a concept here saying that F alpha is always greater than F beta in electronics. So common base bandwidth will be always greater than a common emitter bandwidth. Seeing the board you can understand it. Common base bandwidth will be always greater than a common emitter bandwidth. Now let us understand parameters, let us understand the root 2 concept. These two issues are remaining. Divya Das, how A is inversely proportional to bandwidth. If you want to know the secrets, okay? If you want to know the secrets, थोड़ा formula से बताता हूँ, subject चाहिए तो वो understand हो जाएगा. इधर थोड़ा property बता रहा हूँ first. You take down. If you take the property, next I'll tell you the secret now. How that frequency, bandwidth का technique क्या हो रहे हैं, उनका derivations बताते हैं, आपको समझ में आ जाएगा. Okay? Common base bandwidth is always high in electronics. Common base bandwidth will be always high compared to common emitter bandwidth because common base will have the low current gain, common emitter will have the high current gain. So let us write the definitions of F alpha, F beta and Ft. 3 letters are there. Let us first define the parameters. So if it is completed, let us move to the 3 parameters now. F alpha, F beta and Ft. 3 parameters, first we'll write the definitions for that. So why you have to represent here beta means it's a common emitter bandwidth indication. Who will write F alpha, it's a common base bandwidth because common base we represent it with alpha current gain, common emitter we represent with beta indication. Okay? Like this we are trying to develop the concept. So let us start the analysis based on this. Let us start the analysis. So in the next page, next slide, you can see what is F beta. Now one words in the classes. We call this as beta cutoff frequency. We call this as beta cutoff frequency, which is called bandwidth frequency. We can say beta cutoff frequency, or we can also call it as 3 dB frequency. We call 3 dB frequency. Bandwidth we call 3 dB frequencies. Okay. So you can write a definition here. It is the frequency. It is the frequency at which common emitter short circuit current gain. It is the frequency at which common emitter short circuit current gain reduces by 3 dB of its value. So it is just reducing the gain by 3 dB of its value. Otherwise 1 by root 2 times. Magnitude wise we can say 1 by root 2 times. Otherwise decibel wise 3 dB. You are just reducing your gain by 3 dB. At the time what is the frequency you got? That we call it as F beta. Then Ft, next parameter. It is called as unity gain bandwidth frequency. We call this as unity gain bandwidth frequency is called Ft. Unity gain bandwidth frequency. It is the frequency. It is the frequency at which common emitter, you write here common emitter short circuit current gain reduces to unity. When you fall to unity, it is called, unity can also be called as 0 decibels. Sometimes they'll use the word 0 decibels. What do you mean by 0 decibels? Means 20 log of 1, we call it as 0 decibels. Unity we are converting into decibel scale as 20 logarithmic. 20 log of 1 will become 0 decibels. Okay? Unity we can call it as 0 decibels. So this frequency we call it as Ft, we call it has a good name in electronics. It has a good name. It is called as gain bandwidth product we can call. It is not bandwidth, it's a gain bandwidth product. Because 1 is the gain, bandwidth we are multiplying, so gain into bandwidth we are multiplying. So this parameter will be there for every transistor we can design. Op-amp will have some Ft, BJT will have Ft, MOSFETs will have Ft. So Ft is a common word for transistors, which is called gain bandwidth product, will be given by designer. This bandwidth we can solve with the help of Ft actually. If I know Ft, F beta we can solve it in classes. Okay? So next one more letter is F alpha, which deals about alpha cutoff frequency. Or we can also call it as 3 dB frequency. 3 dB frequency of common base. This is 3 dB frequency of common emitter. So it is the frequency at which common emitter short circuit you have. Now you can write it as, in place of common emitter short circuit, we can write here as a common base. You can write common base short circuit current gain. Short circuit current gain reduces by 3 dB of its value. 3 dB of its value. So one is common base short circuit current gain. Okay. So the common base short circuit current gain, it has reduced by 3 dB of its value. So these are the basic definitions about F beta, Ft and F alpha in the class. Okay. these are the three formulas we have. Just what I need is, what is the interrelation between these two things a student should understand. So a small analysis, low pass transfer function, if you can understand, I can show you the concept now. Transfer function. Somebody is asking, can you explain the low pass transfer function? Okay, how to find out a low pass transfer function? With the help of this, I can explain you 1 by root 2 concept, I can explain you FT concept, all these issues. See the low pass transfer function. First of all, how to design a low pass circuit. Low pass circuit is a simple circuit with RNC components. Just you have to take C at the output, series wise R. So this is called a low pass circuit. One R and one C here. Take C should be in shunt, R should be in series, is a low pass circuit. So if you want a transfer function for this, output by input we can find out. Output by input. We can call this as a transfer function. We're finding a transfer function for this, which will tell the behavior of low pass system, which is 1 by SC divided by R plus 1 by SC. Just voltage division rule I applied. Voltage division rule I applied. R2 by R1 plus R2. R2 here is 1 by SC. So transfer function can be represented as 1 by 1 plus S into R into C, which can be written 1 plus S is nothing but J omega R into C. So this is the transfer function of a low pass systems. Just hardly it's a matter of just voltage division technique. So the transfer function will describe you how the gain is falling in your frequency plot. You have been solved with voltage gain, but it will be definition will be same for current gain also. So transfer function we can use for current gain. If you want, you can use for voltage gain. Whatever you like, you can use. This is a standard transfer function for any type of gains you can apply. So this is the basic transfer function I predicted. So please complete up to here. Just I'll show you the meaning. Why we take a beta whenever you take, why we take 1 by root 2 times there. That knowledge I'll explain. So we are coming close to the concept. Finish first. After that we will go for the last topic that is called voltage gain analysis is the final trick. So today onwards we have to take more time to finish up one by one topics. Up to now we have been relaxed. Nicely we are dealing daily 7 hours or 8 hours maximum. Today onwards we have to keep more efforts to complete the subject. Maybe I'll be more stressed. I'll have more stress, but we can't do anything. When work comes, we have to take a challenge and we have to complete the subject. Okay? We should not feel stressed like that. Whenever it is want to be completed target, we have to reach the target always. Target is important always. 1 by 1 plus J omega into R into C. A small derivations I am showing for you. Links I'll explain you. 1 by 1 plus J omega times R into C is the transfer function we got. Omega can also be called 2 pi f. Omega is the radial frequency. Where omega is nothing but 2 pi f. It's angular frequency we can say. Omega is called as angular frequency. Omega is nothing but angular frequency we say. It is called as angular frequency, which will have radians per second. The units will be in radians per second if you teach about omega. Okay, so I'm expecting it's completed up to here till now. Let's see the final steps to complete the task. Final steps I'm explaining. Final steps, we'll see. Final step. If you take common emitter, short circuit, current gain concept. Once again take this analysis, common emitter, short circuit, current gain. If I want to write my current gain formula, what I can write is HFE is the current gain. Below that you keep the transfer function so that how the gain will fall with respect to frequency we can solve. We got the formula as 1 plus J 2 pi F into R into C. This is the transfer function. So this is transfer function, this is your gain. So how the gain will fall, if anybody asks you, the response is falling. I think this frequency, whenever you are increasing, this is responsible to tell that how the gain will fall at high frequency. So this is my transfer function applied. So this can be written in magnitude if you want. This can be written as HFE divided by root over 1 plus FE dB F by, you write another definition here, F beta whole square. So what is F beta here is, where F beta is nothing but the fixed components 2 pi R into C. That means your bandwidth always depends on the resistor and capacitor component in low pass system. So how much R, how much C, you have to find out in your device BJT such that there are fixed quantities inside the device that will give the bandwidth. So we have been represented this 2 pi RC as reverse answer is F beta. That is your bandwidth frequency formula. 1 by 2 pi RC. 1 by 2 pi RC. So here R, if you want the formula 1 by 2 pi, 1 by 2 pi, it will be coming from input time constant of your amplifier. So input time constant Ri, we can write it as beta Re is the input impedance. Your transistor input impedance is beta Re, and the input capacitance we can write here as CD plus CD. We have two capacitances. I have taken the addition of two capacitances, CD plus CD, which are called junction capacitances. So these are junction capacitance. This is your input impedance. This is R into C value for you. So finally, I think F beta formula is also ready with RNC components. Examiner will ask you the questions based on this RNC values. At the time, this is the formula for it. Just input resistance, input capacitance I have done. So beta Re plus CD actually, but we'll write here not only CD plus CD also we are writing. So what is the reason for that? Why should I write like that? There's some theory for that again. There's one important theory to tell why CD plus CD are written. So this concept we call it as Miller's theorem. So let us understand Miller's theorem here so that in the next topics, wherever I want, I can use this Miller's theorem concept. What is Miller's theorem here is, you can see somebody has given transistor like this suppose. This is collector, this is base. We have some capacitance here, CD, diffusion capacitance. Here we have some capacitance inside, this is CD. Yesterday we have seen our models, pipe model. CD is the input capacitance, junction capacitance, and CD is the output junction capacitance. I have written the board. But somebody asked me, can you tell me what is CIN? Here he is asking, what is CIN? Here's some concept we have to understand. This is not only the capacitance I'm seeing here, this capacitance is also connected to the base. That is called Miller's effect, we say. This point is actually input for us, and this point is output. Therefore, CT in common emitter is not an input capacitance, is not an output capacitance. That is the point we have to understand in common emitter systems. This capacitance is not an input, it's not an output, it is concerned for both. That's why this capacitance we call it as a feedback capacitance in this transistor. CT is not an input capacitance, it's not an output capacitance, it's a feedback capacitance. That feedback capacitance, how to resolve into two parts. Input side, how much you can distribute, how much you can distribute at output will be solved by a technique called Miller's theorem from networks. There is one beautiful theorem for this called Miller's theorem. What the Miller's theorem says that whenever you got this problem, input, output, you have two points where some jet is connected between these two. This is jet. We have some jet here, input to output. And there's a common ground, which is your emitter. Then he's telling that we can just resolve this problem like this. This network we can easily resolve as this is input and this is ground. We can make it input part as input impedance. Jet1 we can make it. And output side we can make output impedance. That is jet2. So like this you can resolve. This Miller's theorem is telling for us. This Miller's theorem is one of the best theorem we'll be using for coming classes in biasing techniques. So let us keep it formless for this so that we'll understand why this person written CD plus CD. I'll prove it for you. Miller's theorem says that the jet1 answer here is jet1 formula is jet by 1 minus AV is the formula. Jet by 1 minus AV. Jet2 is jet AV by AV minus 1. Okay? Otherwise you can practice like this. Similar practice but you do it like this. It is 1 minus 1 by AV is the practice. So this formula looks easier only, not a big practice. So jet1 is jet by 1 minus AV. This formula to this formula if you see output side, same formula, just 1 by AV you write there. 1 minus AV is first part, second part is 1 by 1 minus 1 by AV. A derivation both asane, but we are not interested in derivations, we are interested in the results. Let's see with this result how to get this capacitance impact here. This capacitance impact here may be resolved as like this. Is CT1. This is the input effect for that. If I resolve this capacitance effect, this side will get CT2. Like this I want to resolve this capacitance. Such that you can neglect this one, we can show both sides. Okay? Now what is CT1 if you want? That is jet2, this is CT1 you want. So first formula you can write. Jet1 is jet by 1 minus AV. You can take as first formula. But we are not interested with impedances, we are interested with capacitances. So how I'll do is 1 by j omega CT1 I'll convert. In place of jet, we are converting into reactance. 1 by j omega CT1. Jet is nothing but 1 by j omega CT. It's a middle capacitance into 1 minus AV. Can you see that j omega is cancelled? Then what is CT1 here is? It is CT times of 1 minus AV is coming. So this is called as Miller's capacitance. Very important topics there. Exams they'll ask you here, what is CIN? Don't say CD here. Okay, there's one important issue here. CD plus CT1 is coming there. Whenever you have two parallel capacitors, we just add it. Series mein add karte ho. So CT1 plus CD will be the total capacitance due to this Miller's story. One of the important concept it is. So I have to teach here compulsory, that's why I'm teaching this points. So CT1 I understood. It is CT into 1 minus AV. Okay. Now I think the story of CI, you can see. Story of CI. CI became the formula, CIN became the formula CD plus your CT1. This is CIN according to our formula. But CT1, what happened is, it is CD plus CD into 1 minus, again I applied here a sign called minus AV because it has 180 degrees phase shift. Your common emitter will give phase shift. Again the twist came. The gain is not positive, the gain is negative because minus GM into RC we are getting. So apply the negative sign such that the formula becomes CD plus CD into 1 plus AV will come. Okay. But in this concept what we done is, we have taken load is 0, that is short circuit we have done for doing current gain calculations. RL equals 0 current concepts. When RL is 0, then I think your AV, which is V0 by VIN, will become 0. So voltage gain will become 0. As load is 0, voltage gain is 0. Then automatically this formula becomes CD plus CD. Can you see that this much information is there to tell you one single line here in analog electronics? So finally, you should not get any confusion now. It is not CD, it is CD plus CD as your input capacitance. If I don't teach like that, what happens? You feel that this is output capacitance, this is input capacitance. There is some capacitance is falling to me technically that is being resolved by Miller's theorem and finally understood it is CD plus CD into 1 plus AV, but AV is 0 for these calculations because load is short circuit. So finally the answer should be written CD plus CD. So this is the story about the concept. So please complete this new package formulas. Very interesting the concept. So in the coming class for two problems whenever I have Miller's concepts, I just use this formula and I'll finish the concept. I use just this formulas. So don't ask me again and again what is this formula. So here content is there, you can stop practicing it. Only two formulas here. Jet by 1 minus AV is input impedance effect. Jet by 1 minus 1 by AV times is your output impedance effect. Right side is not visible. Just I'll make it like this. Now you can see. So please complete it. Sneha Kumari and Swati, just I compress the video. Just you can see. Slide is compressed. We'll finish off. Come on, fast. So this is about the story of RIN and CIN story. RN we know that is beta RE, which is called R pi. But the CIN is a new concept we have studied. Who is this fellow? Bikash Kumar. Why 180 degrees phase shift you are asking after completion of the total course? After completion of the total course, you are asking why it is 180 degrees. Your gain is equal to minus GM into RL. This minus signifies 180 degrees phase shift for common emitter. Are you seeing some minus there? Every time in the formulas, then the derivations minus is coming. What is that minus signifies? If input is low, output will get high, amplified by high. If input is high, output will be amplified in reverse manner. That is called phase shift. Divya started to ask me what is beta is RA कैसे हुआ? अरे why you are asking that question? You are see here ये क्या है? अभी तक क्या किया यार? What is this? It is R pi or not? Input impedance क्या होता है inside? R pi. R pi can also be called what? 1 plus beta RE. In place of writing 1 plus beta, I have written beta RE because for approximation most of the times we write beta RE. This answer we can write it as 1 plus beta RE, which can be simplified as beta RE. Okay, that is a common sense I have written, nothing is there. Beta RE I have written. So if you complete this part, let us move to final concept now. F beta we got, all the stories are over. So keep this formula in practice. You have to do the problems now in workbook with these formulas. 1 by 2 pi beta RE into CD plus CD. And make a star mark. These two formulas are important for my next typical problems I'll solve with this Miller's theorem effects. Z by 1 minus AB, one formula. Z by 1 minus 1 by AB is another formula. These are the simple formulas we can use. Okay, Divyadas, I hope you understood. It's a great thing for me. So let us close the matter. Let us close the matter. The current gain, you got the formula as HFE by under root of 1 plus F by F beta whole square we got. Now suppose if I apply condition, your F is exactly reaching to F beta. Your bandwidth and my frequency of operation is same. At the time, what happens? If F is reaching to F beta, then what happens to current gain? It becomes HFE divided by root over 1 plus your frequency also became F beta by F beta whole square. It becomes HFE by root 2. Can you see the story of minus 3 decibels? So why these people will take means there are some reasons for that. There are some reasons like that. If you get the answer 1 plus 1, you cannot neglect 1. 1 plus 1 are there, you cannot neglect 1. So whenever you reach to the bandwidth, exactly at that frequency, 1 plus 1 will come in the transfer function. It will become root 2. So exactly by root 2, practically we take the bandwidth. So this point is a very common point. Who is practicing GATE and ESC? For electrical or ECE, this is a very common sense point. Communications may, you will study these things. So you don't see newly whenever you see these bandwidth concepts. Okay, it's a common sense. 1 by root 2 times you have to follow it and you have to take the bandwidth. That's why they call 3 dB frequencies, these points. So first I hope you resolve the concept. Suppose the second one, your F is reaching to FT suppose. At that time, your current gain became 1. There is another condition applied. Your F is reaching to FT, unity gain bandwidth frequency, it became 1. So current gain, you keep it 1. HFE by under root of 1 plus FT by F beta whole square you can take. FT by F beta whole square you can write. But we understood that your FT is much greater than F beta in the problem. Your FT is coming more than F beta because F beta is the frequency we got when the current gain is 100. But FT is a gain we got at 1. As the gain is low, bandwidth will be more. So FT is always more than F beta. So because of this ratio, we can write it as HFE by under root of FT by F beta whole square. Can you see that 1 is neglected in the problem because this quantity is becoming high compared to 1. So this square and root will be cancelled. So can you see the formula again? A beautiful formula. 1 into FT is equal to HFE into F beta. So this is one of the golden formula in analog electronics. It's a golden formula. Throughout your life, it is not possible to forget these things. Very standard terms. 1 into FT is equal to HFE into F beta. Somebody asked me a question, sir, if gain increases, bandwidth क्यों decrease हो रहे? आप भी देख सकते हैं? For example, HFE given in the problem is 100. Your FT is given in the problem as suppose 10 power 5. So otherwise, we'll take this as some 10 power 3. Your gain bandwidth product is given as 10 power 3. HFE is given as 100. So if you see the story now, if I want to find suppose F beta, which is called bandwidth, I want to find. These are the basic questions you can do in electronics. HFE given, FT given, F beta is asking. Then we have a formula here. 1 into FT is a gain bandwidth product is equal to gain into bandwidth again. Gain into bandwidth. So gain is HFE F beta. So 1 into 10 power 3 is equal to 10 power square into F beta. So F beta, if you see, it will become only 10. So can you see that as the gain is 100, your F beta is only 10. So that itself is telling about the story that current gain, if it increases, your bandwidth has to decrease. This is the proof for that. So ultimately what you want to tell is FT is constant for a device. If you increase on the other side, one parameter will increase, other parameter will decrease. That's why in analog electronics, it's a common theory for us. As the gain increases, bandwidth will decrease. As the bandwidth increases, gain will decrease. That's one of the basic knowledge will come from this subject. So this completes the story about the analysis called EI increases, bandwidth will decrease. So you have a sort of workbook questions based on this. So you should feel comfortable by saying these statements. 1 into FT will be always equal to HFE into F beta. There is maybe one more formula also they may ask you. For that a small conclusion, no derivation for that. It's an approximation formula. If anybody asks you, suppose F alpha is asking what is the formula is, it is approximately 1 plus HFE into F beta. So this is only an approximate formula. By chance if they ask you F alpha, you can give this approximate answer. So what it is conveying is, it is F alpha is telling I'm slightly greater than FT. I'm slightly greater than FT because FT we are taking at 1. But F alpha we are taking 1 by root 2 times. That means the gain is falling by 1 by root 2. You are getting the FT. So FT will be close to F alpha. Very close to each other. So increment of 1 will write. By chance if the examiner asks you F alpha, you just increment it. If beta is given 200, suppose 201 times of F beta will be the answer. Okay? So this is an approximate answer with the help of this we have written. So this completes all the formulas related to this subject. So with this I completed the story of current gain analysis is completed. But the main analysis is not current gain. Voltage gain analysis is the final task to understand. Let us able to understand the final issue now. Voltage gain analysis is the final concept. Rahman, you should not say different model, you should not say different transistors you have to tell. Different transistors will have different FTs. Okay? Suppose your transistor gain is different, my FT will be different. If the transistor gain is for two different transistors, 2 different gains, we'll have 2 different FTs. Okay? If the 2 gains are same, then we'll have the same FT. That depends on the gain actually. Sir, is there any formula you can create for FT? Yes, we can create. F beta, we got the formula as 1 by 2 pi beta RE into CD plus CD. This is the formula we got, F beta. Now you can see the formula of FT. This beta, whatever you are seeing this beta, suppose if I shift here, if I shift that beta here, then I think HFE into F beta is FT. FT becomes beta times of F beta. Beta times of F beta is equal to, can you see this 1 by RE, we'll write it as GM. by 2 pi CD plus CD. This is one of the standard formula for gain bandwidth product. This is called gain bandwidth product, which will come from FBW. This is the trick for it. So gain bandwidth product, if anybody asks you the questions, just move this beta here. Then you'll get the formula 1 by R equal हम GM convert करके complete कर दिया. So this is the total story about your analysis. Just 45 minutes give me the time to complete the voltage gain analysis so that we can start a new video after the break. All workbook problems will finish today. Okay? So a lot of questions are there in common emitters. So each and every question to explain hardly takes maybe 2-3 hours time. So we'll spend the time for 2-3 hours, no problem, so that we'll get the clarity of each and every question in the amplifiers. Today my job is to complete that problems also today. Tomorrow morning we'll finish that other two amplifiers, and maybe tomorrow only we'll start a new module also. Slowly we'll increase the speed level. Multi-stage also tomorrow only maximum we'll try to cover. Okay? Tomorrow onwards we don't want to take rest, we want to complete it. We'll take very good number of hours to complete the subject completely without leaving anything. Okay? Maximum we'll complete all the issues. At the end, I already told you some topics like triple five timer and active load, active filters. These topics I'll give as presenting as a recording video for you. The remaining things I'll explain each and everything in the notes. The two videos are lengthy concepts, so I'm giving as a presenting as a video for you. In every batch, I'm doing that only because time is going more and more to teach each and everything in analog electronics. So at least the two topics if I do a recording video, it will balance my timing for me. I'm taking so much of time other than what they have given the schedule for me. The only reason is the student has to get confidence on the subject. That is the main reason. I've taken some extra hours to complete the subject. At the end, you should feel happy that each and everything we have covered. What book also step by step we are covering. That is a good thing in our class. Majumdar is enabled here. In between, suppose anything is there, input will have that effect, output will have that effect. Technically, we'll resolve in both sides and we'll study the subjects. Middle में नहीं रखते, उनको input and output को resolve करते. The theorem we call it as Miller's theorem. With the effect of that, we are studying the concepts. Okay? Chalo. So this completes the story. Let us start the final story today. That is called voltage gain story. Voltage gain versus frequency. When you study voltage gain analysis, we'll take the complete amplifier now in the class. Current gain means only transistor wise we have studied. Now, voltage gain if you want to study, voltage gain versus frequency. Voltage gain versus frequency. If you want to study, you have to take the complete amplifier design. We'll take a RC coupled amplifier, we call this as RC coupled common emitter amplifier, which is called voltage amplifier. The name of this circuit is RC coupled amplifier, also we can call it. So how it looks RC coupled amplifier, you can see this is your voltage source. We have some resistance here, RS. Next we have CC1. Next we have transistor with RE. Take some capacitor here, CE. Here we have RC. We have biasing circuit here, R1, R2. This is VCC. This is a capacitor, CC. This is your output V0. So till now we have seen this amplifier, where there will be three capacitors will play the key role. I said in previous class with some basics. CC1 is playing a role of AC/DC mixing. CC2 is disconnecting the DC and giving the output. This is bypassing the current, AC current, where it will nullify the negative feedback effect. So these things we have seen step by step clearly in previous class. This is called as RC coupled. It's called RC coupling, we can say. One R and C is coupled here. Okay? RC coupled amplifier, which is a very big size amplifier. It is RC coupled amplifiers. So at class, what we have to learn from this techniques, try to see. Actually, in the exams, they'll ask you frequency response. First point. Seeing the board, I can write the frequency response like this. This is your frequency response. F versus voltage gain. You can see the response is coming differently. As we studied with the current gain, voltage gain response is coming different. Voltage gain response is coming like a band pass response, but previously we got low pass. Means we have studied only BJT, that's why we got low pass. But we are studying circuit and BJT, both we are studying. Here BJT also we are studying, here circuit also we are studying. When you study like that, we get band pass response. What is the band pass means? In the mid frequencies, the response is good. That is called band pass response. You take this as AM, mid band gain. You have some mid band gain, AM, it's called mid band gain. And it is being divided by, same story, 3 decibels we have to reduce every time if you want bandwidth. So the bandwidth will come between FL and will get in between FH. These are your 3 portions. There will be 3 portions in the frequency response. So one is called low frequency, one is called mid band, one is called high frequency. So let us keep this marking as low frequency. This is called low frequency from here to here. This is called high frequency. Low frequency is there, high frequency is there. And here we have mid band. Here we have mid band frequency. So this is the way you are seeing the frequencies. Low frequency, mid band and high frequencies. Now if anybody asks you why this attenuation is happening here gain, why this attenuation is happening in the gain, somebody asks you, you have to tell that which capacitors are creating problem for that. That is the concept. You just have to have a knowledge which capacitors, what conditions they are. That points now we are going to elaborate. You can see below this I'll do the boundary techniques. This is your FL, one boundary. This is your FH, another boundary. We have 2 boundaries here, FL and FH. Okay? Below this, you consider it as a low frequencies. Whenever you consider low frequencies, we know that we'll assume CC and CE. On the board you can see CC and CE are called circuit capacitances. That is all circuit capacitances. We call external capacitors CC and CE. We are assuming it as open circuit for low frequencies. Not only that, we have 2 more capacitances here. We call this as parasitic capacitances, I said. One is CD and one is CD, which are called internal capacitors of your BJT. So you can write both. Here, CD and CD. This also we are assumed as open. Because when you are talking low frequencies, all capacitors will be assumed as an open circuit. It may be an internal capacitors or it may be external capacitors. We just take open. That is the first idea. Okay. Next, when you come to high frequencies, we assume that CC and CE are short circuit will assume, and CD and CD will assume it as short circuit. So when you are close to zero frequencies, it's an open circuit we have taken. When you are close to high frequencies called infinite frequencies, then you have taken short. Now you have to tell me, seeing this board, this all capacitors, if you open here, if you open all capacitors in the board, which capacitors are creating problem for your amplification, you have to understand from the board. It's a very simple thing actually. You are sending here signal current. You are telling that this is open. When CC1 is open, I think that the current cannot go to the transistor to amplify. That means this capacitor is creating problem there. Coupling capacitor is creating problem. But these capacitors, if they are open, that is happy for us. Because if the capacitors become short, R pi will become short, impedances will become zero. So capacitor should not short inside the device. Inside the device, opening is better. Outside the device, short is better. So two different issues are going on. So what is the technical problem here now? Identified is, this is the problem. This is creating the problem at low frequency. Because of this, your voltage gain is decreasing with respect to frequency. Means you are talking this side. When you are going this side, close to zero side, lower frequencies, because of this coupling and bypass capacitors, the gain will fall down. That is the main reason here in the concept. In a similar manner, here high frequencies if you come, which is creating problem here. Again the gain is falling here. When you are going away the frequencies of FH, can you see that this is short we have done? Nice, current will go. This is short, your R pi will be zero. If R pi is zero, you will not have any gain output. So this will become short, will affect the BJT. So this capacitor is affecting, but this capacitor is not affecting. So I think your junction capacitors are creating the problem here. So this is the way how I identify the conditions for capacitors. In one area, external capacitors are creating problem. In one area, internal capacitors are creating problem. So because of this reason, your gain again decreasing. So both cases, the gain is getting attenuated because of two different capacitors. But in the middle, why this person is enjoying the mid-band means maybe the reason is these capacitors, whatever trouble came, when it comes to this boundary, maybe it has changed its behavior after passing this boundary. The CC and C are open circuit below these lower frequencies. When you are above that frequencies, we consider it as high frequencies. So we'll get like this. CC and CE will be considered as a short circuit. That means for these capacitors, above this FL only we are considering they are short circuits in the classes. Means we are designing that capacitances in such a manner, they'll work like a nearly short circuit from this frequencies onwards. Therefore there is no trouble about this concept. The same story again here. Below FH, above FH it is creating problem, CD and CD. But below FH we design in such a manner, these capacitors should behave. These capacitors should behave like CD and CD should be open circuit only they have to behave. So I have seen the boundary technique now. External capacitors when you cross FL boundary, they'll become short circuit. When internal capacitors when you cross this boundary FH, they'll become open circuit. They'll become open, if you go that side, it becomes short circuit. So FLs are meant for to design these capacitor techniques. FH is meant for to design the internal capacitors. So examiner will ask you the questions related to FL how to design, FH how to design. These are today final class. Just today I'll not give any derivations for you. Just a trick I'll tell you, seeing the board how to remember the formula. For this I can do it separately the derivations if you want. I can make a derivation for it and I can post it for you in your WhatsApp group. And not only that, in PDF format also I can send for you. But today just I'll do the trick based formulas without doing each and every derivation. It takes a lot of time for me. So just formulas I'll explain you. That formula is more than enough to solve the questions. How to remember the formula is the best trick that I'll explain. So with that I think by 1:30 we can finish up. Within 15 minutes I'll round up the formulas. And finally we are closing the matter of total analysis, common emitter amplifier. We are ready. So we can be starting attacking the problems from 2:30 onwards. Okay? By 1:30 I'll stop the class. By 2:30 we are going to start. 2:30 to 5:30, 3 hours we'll spend the time to complete all the problems. Then we'll stop the class. Okay? Today class up to 5:30 can go for two problems. Let's see. So nicely write down this story. So we are getting here also no response is not good. Here also response is not good. Only in the mid band we are getting good response because external capacitor short is better, internal capacitor open is better. That is happening only in mid band range in electronics. So nothing is short, nothing is open. It is an approximation. They are nearly short, they are nearly open, like that we are talking. But how to design this FL and FH formulas? That is important. You may get some questions based on that formulas. The very easy formulas. You do not take much headache to write the answers. Simple trick I'll tell you. With that we can finish off. So please complete it. Last formulas I'll explain you. We need high frequencies and we need low frequencies. Two things I have to explain. FL and FH, how to calculate. So maximum 100% I think all the things we covered. So you're ready to attack the problems. Any question we can do it now. I think first before starting the class, short notes will be there for half an hour. I'll get good short notes now. Whatever we studied till now, how to make it as a package, how to study. The good notes will be there. After that we are attacking each and every question. So spending for half an hour or 45 minutes max to get the total short notes in the class today. Okay? Short notes will help a great for you to finish all these things. Because yesterday onwards we are doing. Today we completed. So taken per about 1 day, 10 hours it has taken this content. But the 10 hours how to study within half an hour or 45 minutes, I'll show you the concept. This topic must be the best topic in analog electronics. So I think I completed. Just we'll see the final analysis now. Coming to the final analysis. That is design of FL. Design of FL. FL means in my sense lower cutoff frequency. Lower cutoff frequency we call. Lower cutoff frequency. Side by I'll explain you. Design of FH. Side by we'll complete this also. That is called higher cutoff frequency. Higher cutoff frequency is very easy. Seeing the board we'll get the answers. Here a small trick I have to explain for you. So for this we'll take the diagram to write answers. This is your VS. This is your VS. Only AC model you write first. AC modeling if you write, there is RS here. Don't make short, keep the capacitors to answer the question. CC1 you keep it. As AC model you are talking here, this will become RP ground. VCC will be grounded, so RP will follow. The next we will have here, transistor will be there. We have some resistor here, RE. We have one capacitor here, CE. Keep all the capacitors in the model. This is RC. This is ground, VCC. Capacitor, CC2. And finally we have the load. In the exam, if I see the question like this, how will I write the answers in a simple manner? You can see. How many time constants we have here means this is one time constant, this is one time constant, this is one time constant. In the heading I have written only FL, but we are getting 3 FLs in the class. This is 1 FL, this is 1 FL, this is 1 FL. FL is nothing but what? 1 by 2 by RC. So today our investigation is R equivalent how to find, because here R is connected to certain resistors here. So what is the FL formula here is? The secret is simple. It is 1 by 2 pi R equivalent in the circuit into C. Particular C if you talk here, CC1, but R equivalent we don't know. We have to practice it now in the class. Okay, we have to do it. What is the trick based concept you can see? The first formula, suppose this is your first formula I want to teach here. FL1 will take, this is the first lower cutoff frequency. Okay, FL1 if I want to write C in the board, FL1. So please remember one trick for this. When you are solving here, these 2 capacitors should be short circuit. The other 2 capacitors you have to keep in mind that they are not included in the circuit. So if I am teaching FL1, the condition is this is short, means this is a short. We have here some R pi is there. This is R pi is there. Then if it is short circuit, this is a ground. So these 2 parallel will come. So see the formula. It is 1 by 2 pi CC1 up to here is over. Only thing is R equivalent you want. This person got the answer like this. R is plus RB parallel to R pi. Are you getting any trick seeing this formula? How to remember this trick? After doing the total derivation by using AC analysis, this is the formula I got. Is there any trick means? The trick is RS plus RB parallel to R pi. This comes in series mode answer. You have to just make it series that answer. This is RS, this is RB parallel to R pi. At the time this is short circuit. So like that you can instantly answer the question. That is the standard formula. How to remember? I have said the trick for you. RS plus RB parallel to R pi. That is our style of remembrance. In the next formula if you see here, FL2 suppose you want. The formula we got as 1 by 2 pi CC2 into R equivalent is RC plus RL we got. Then you can think here also the same trick is happened. These 2 are in series we got. So coupling capacitor wise who is solving the class is getting the addition of the 2 components. Before and after we are getting addition here. This trick is very easy to finish the problems. It will not take much time. So derivations are not much important for this class. Formulas are important for me. So to attack the question. So this is my 2 tricks. I think these are comfortable only. They are not big issues to remember. Both should be added always. Okay. Here also you add it. This network will add karo. Add this network RC plus RL. But here if you see one special technique. What is this answer is? This is emitter. In actual load we have learned one trick for this. If I want to know at the emitter inside what is Rx? We have been studied the concept. Inside Rx, inside what is there? Rx value means it is 1 by Gm will come here. Inside the emitter we study actual load techniques. So without doing all these stories, straightforward I'll write the answer. Your FL3 will be 1 by 2 pi into CE you write. But here Re is there. Inside resistance is Rx, this total resistance, which is nothing but emitter side whenever you teach, it will become 1 by Gm. I have proved in my classes in actual load techniques. So that knowledge we can apply straightforward here without doing the derivations once again. Okay, unnecessarily don't increase your energy levels for this analog electronics. One time you investigated, use for everything there. Whenever you wanted emitter, the answer is 1 by Gm. Approximate answer is 1 by Gm. So Re plus 1 by, sorry it's not plus, it will come parallel now. Re parallel to 1 by Gm. Re parallel, this is Re, this is parallel. Inside parallel combination is 1 by Gm. So this is a typical formula for your FL3. So Re parallel to 1 by Gm. So after completing these 3 formulas, we completed the first job. This is 1 FL1, this is another FL, and this is another FL. So which is your FL means, from all these 3 calculations, which FL will come more, that is your FL. Okay? From all these FLs, which is the highest one, that will be your FL. That is your FL. Last one, the same formula, the same diagram, if I write AC model for higher frequency techniques. For higher frequencies, how the model will come. You can see, this is VS, we have RS. Now you make this as short, because at high frequencies, CC1 will become short circuit, and here RP will be there. Next to RP will be there. Next we have some capacitance will be there, input capacitance CIN, Miller's capacitance, and we have current source, GM into V pi. Next we have some RC, next we have some RL. This is your output. This is CC2. So correctly see the board, how I have written high frequency model, is easiest model. First VS, next to RS, CC1. High frequencies may, capacitors already became short circuit. CC1 became short circuit. Next to RP will be there, RP will be there, this is totally short. Up to here, okay. Inside there is some Miller's capacitance. We are talking about internal capacitance. So Miller's capacitance I have written. CIN, we study CD plus CD into some 1 plus AB. That is CIN. GM into V pi. Next we have RC parallel to RL. This is short circuit. Just you write the model presentation like that nicely. Okay. One time if you can complete that model, just writing the answers are very easy. Suppose if I want to find from here, your FH1. Suppose I want to find higher cutoff frequency FH1. You have some time constant here also. FH1 formula is 1 by 2 pi CIN. CIN is there here. 1 by 2 pi CIN into this all resistors will be parallel. RP parallel to RS. If you see here, this output resistance we are solving from this network, this is short circuit. So this 3 will become parallel always. That's a simple formula. Okay, that's a simple formula. So this is the story how to find out FH1, higher cutoff frequency from the input circuit. Where CIN is nothing but CD plus CD into 1 plus AB. And AB you keep in modulus because minus of minus, I made it as positive. So modulus may roko. It is called Miller's effect. It's called Miller's effect. So this is called FH1 formula. Same thing you can do for FH2. If you want FH2 answer, Second answer is FH2. Confined from here, FH2. It is 1 by, I think here one capacitor is here, one capacitor. That is CD you can write. Output capacitance you can write CD. 1 by 2 pi, 1 by 2 pi, it is C naught output capacitance into this equivalent parallel resistance is RC parallel to RL. There are parallel combinations where C naught will be equal to CD. Where C naught is equal to CD. Transition capacitance will come here. So these are the entire formulas. In a single page you can practice all the formulas. FH1 you want, FH2, FL1, FL2, everything is there in the board. Just these formulas you have to practice. Conventionally when you are doing for conventional subjects, we need derivations also. But at this level, I cannot teach you derivations for this topic. Just only orally you just practice these formulas, which will help us to solve my objective questions. Okay, this is more than enough. No need of derivations also, because you are studying an objective student, no need of derivations. Just practice the techniques. CC1, CC2, we have to take addition of the resistors, and here we get parallel, and the other two cases also we get parallel combinations. These are the 5 formulas you have to keep in practice. So with this we have completed successfully. Now the time is around 1:30. Around 2:30 start with the class. Okay, around 2:30 I'm going to start a practice session. Workbook practice will be there. Workbook practice. We'll see today we'll complete these total problems. Workbook practice. With that our job will be completed successfully today. Tomorrow we can start freshly. Common emitter and common base amplifiers. Tomorrow we'll finish off. Okay. So please complete it. I'm taking break for 1 hour now. Around 2:30 sharply I start the class. So this is the complete formulas you can note on the notes. Okay. So I'm leaving just 1 hour. I'll relax for some time. 2:30 start with the class. So streaming will be like this for 10 minutes. You can just note on it. After that you can take a break for 1 hour. I start at 2:30 the class again. Recording.